Hi, I'm Lennart Vattering. You might know me from systemd and stuff. I'm going to talk today about casync, which is my little side project. What's very unfortunate is that exactly at this time, or like in 20 minutes or something, there's another talk about casync actually, somewhere on the other end of the campus. I would much rather be at that one actually, but anyway, for the ones who might have seen this talk, like for example at All Systems Go or DEF CONF last month, it's probably a good idea to go to the other one and you learn something new, because this one's just mostly the same slides as before. A little bit updated though. Anyway, I'm talking about casync. Yeah, let's jump right in. What is casync? The name casync is supposed to suggest the relationship to content addressable file systems. Oh, by the way, if anyone has a question about any of what I'm saying here, I much prefer if you interrupt me right away and we have a discussion on topic than doing all of that at the end. So by any means, you're completely welcome to interrupt me. Yeah, casync, content addressable file systems, everybody knows those, like Git, like everybody of you probably plays around with Git every day. You know how this works. Content addressable file systems are these things where you have these hashes and they refer to objects, and then you can use these hashes in place of the objects, and then you can build trees and these kind of things of that. So that's one concept that casync picks up, and the other one is Rsync. Pretty sure Rsync, everybody knows that too. What most people don't know, probably who use Rsync every day, is the actual smart part about the algorithm about that. It's the Rsync algorithm. The Rsync algorithm is something that only actually happens in Rsync if it realizes there's the same file on both sides, like on the local side and on the remote side. Then the actual smart part of Rsync takes place, which is that it tries to figure out the differences and recognize the same data blocks in those files, even if they shifted in the file by variable amounts of bytes. So yeah. Rsync is an awesome technology, and like I think it was originally written in 1992. The ideas behind that, unfortunately, never became standard in what people do. I mean, there are lots of projects who use the Rsync algorithm, but unfortunately, there are also a lot of projects that should use it that don't. Yeah, it's an interesting little algorithm. We'll talk about that later on. So this is the combination. Of course, this doesn't really say much. So what is it actually? I call it a content addressable data synchronization tool. So it's a little bit like Rsync and a little bit like Git, but it's also not like Git and also not like Rsync. Its primary use case is file system, like it can synchronize file system trees for cases where you have many similar trees. One major use case, and the original one, the one I cared about the most initially, is about delivering OS images. Like OS images meaning container images, VM images, IoT images, whatever you want to call them. Something large that you tend to update in pretty regular intervals, but mostly stays the same except for a couple of things that you like fix a bug in or add something, right? Yeah, OS, container, IoT, VM, whatever you call it. It has two other use cases though that I'm mostly focused on like adding functionality for that right now. Which I think are pretty much the same. Actually, it's the synchronization of your home directory between systems, or backup. Backup, of course, is very similar in some ways, but also different in others. It's similar because you actually also focus on large file system trees, like for example your home directory, which mostly every time you want to do backup stays the same, except for the few places where it doesn't. Right, so and a backup system that wants to be efficient should take benefit of this. Of course, if people back up their stuff with tar, that's not very efficient because every time you tar the whole thing up. So it's first of all, it's very slow, and secondly, you store a lot of redundant data. So yeah, these two use cases, image delivery and backup / home synchronization, are different, but I think they're like similar enough so that we can cover them with the same program. casync can operate on two layers. Like which one you pick is up to you and depends on your use case. First of all, it can operate on the block layer. So the data images that like the OS images that it delivers to systems, can be basically what you DD of a block device, right? Like so raw ext4 image, like the actual blocks of the ext4 image, or squash.rs image, or whatever you like. Secondly, it can operate on the file system level. In that case, it looks at files and directories, right? Like your home directory. So that's a level further up. In that case, you're independent of the file system used in the below, to some point at least, and you just look at more structured data in a tree form. So what does casync actually do? Understanding that is like the core of this talk. Is first step, what it does is it serializes everything. If we operate on the block device, that's pretty easy, right? We just read it off the block device. It's already serialized. If we operate on the file system level, it's also something that everybody does all the time, which is tar things up, essentially. I don't actually use tar for some reasons. That's one of the reasons I care about reproducibility. And tar has certain issues with that. Like reproducibility basically means that if you have one file system tree on your disk, that you get the guarantee that serialization of it is exactly one thing and one thing only, and does not change depending on which day of the week you do the serialization on, or what the backing file system actually is, or anything else like this. Generally, tar is not very good at that, because in tar the files inside the directories, they appear in the order whatever the file system decides to push out, and that might depend on many factors, including hash algorithms and whatnot. So anyway, CA-tar, like that's how I called my serialization format. Like all the things that I came up with here always start with the two characters C and A. But the CA-tar thing is essentially just tar. However, it's reproducible and well defined in that. And secondly, it's random access, right? So that if you want to access some file at the end of the serialization, you don't have to read all the beginning like you have to for tar. But for the sake of discussion, let's just assume it's the same thing as tar. Yeah, on the block layer, easy, just read the block after block, and on the file system layer, almost as easy, just tar it up. That was the first step. Now we have this long serialization. Starts somewhere, and it's just a series of bytes. Now we split it up in a way like how the Rsync algorithm does. So we take the serialization, chop it into a series of chunks. These chunks do not have the same size all the time. The size is a function of what's in the data. What's actually happening there is that there's this is the Rsync algorithm ultimately. Is the hash function is calculated basically for every set of 48 bytes of the stream, and when the resulting hash value holds in some mathematical expression, which is hash function modulo q equals something, then we do a cut. What's the effect of this? This effect of this is that same data results in cuts between these chunks at the very same places. Why is that interesting? That is interesting because if we would actually cut in equidistant intervals, right, like we would always cut after, I don't know, 64K, and you insert one byte to the front, then all the blocks through the rest of serialization would change too, because they all get shifted a little bit to the right. And this will happen all the time, because again, like most of the time we talk about a tarring here. So if you add one file in the front, yes, sure, you added a couple of bytes to the front, so all the blocks in the end would change. This algorithm, the Rsync algorithm, like this chunking stuff, has the effect, same data, will result in the same chunks, will result in the same chunking locations. That basically means that if you insert a byte somewhere and remove a byte somewhere, it does not explode into the rest of serialization, but it will change this one block around it, but after that block you get back into the normal chunking that you had before, right? This is like the interesting bit about it. It's what like deduplicating file system, at least the good ones generally do. It's what Rsync does, it's what, what's it called, Dropbox does to some degree, and it's the interesting bit about it. So, summary again, first step, serialize everything. Second step, slices up into little chunks. Yeah. Why do we do this? Yeah, for the adding extra byte in function ripple up to the rest of it. The used algorithm that we use for this is buzzhash, which is a cyclic hash function. It's ultimately just an implementation detail that we do this. The good thing about this is that it's relatively cheap to calculate, right? Like we don't, like, I mean, think about that if we actually wanted to calculate the 48-byte window over the entire stream and shift it along there, we would calculate a lot of stuff. The fact that we use buzzhash makes that much cheaper for the common case. Yeah, this is what I mentioned here, like you use the hash that you calculate for each of those 48 bytes, take it modulo some value q, and check if it's q minus 1, And if it is so, you place a cut. If not, you continue, calculate the same thing for the next byte. If that holds, then you make a cut. If it still doesn't, you go to the next one, and so on and so on. By picking this queue the right way, you can select the average chunk size, right? Which the idea basically is that, yeah, in average I want a 64K block size, chunk sizes, but they can be a little bit smaller, they can be a little larger, it's fine, as long as the average is 64K. That was the second step. Third step, after we chunked it all up, we calculate a strong hash function. Like these bus hashes is like, we forget everything that we did about the bus hash thing, about this rotating hash function. It's not a strong hash function. We only used it for chunking things up. We forgot that now. In the third step, we use a strong hash function. The one we're actually using is SHA-512-256. It's not so well known a member of the SHA family. It's basically SHA-512 but cut to 256 bits. And the reason why that's a good thing is because it's a lot faster to calculate than SHA-256 on 64-bit processors, which is what we mostly have. It's not really SHA-512 cut to 256 bits though, because it actually starts with a different value, start value, so it actually results in different values. Anyway, long story short, it's a strong hash function. It's like what Git uses SHA-1, we use something a little bit more modern ultimately. When we hash these chunks, we then can use the hashes as identification for the individual chunks. Now, at the same time as we do all this, we write out an index file. That's how I call it, which is very simple. It's just ultimately just a list of these hashes. Actually, it's not just a list of hashes because I want random access. And random access to the serialization stream is a little bit difficult if every chunk has a different size, because you never know. If I want to go to byte 5 million in this serialization, then you would have to, that would be O of n, and that would suck. So actually, it's just a list of offsets with the right hashes. These index files are sufficient, like they explicitly define one version of the tree, very explicitly, because all you have to do is like, the hashes refer to chunks. If you concatenate the chunks in the order that the index file says, you're back at the original serialization. Fourth step, after we did all this and wrote out the index file and have these chunks, we compress the chunks individually. So we just use some standard like compression, like a ZSTD, this Facebook fancy compression algorithm that everybody likes these days. Then every single one of those chunks, which are, as mentioned, uncompressed, they're around 64K. We place them in one big directory, and this is what we call the chunk store. We place them in the directory where each file is named after the hash. So now you have basically one big directory with lots of little smart files that are individually compressed and whose names are all hashes. And then you just have to pick out the right ones in the right order, and you're back at the original serialization. And that's all that casync ultimately does. To recapitulate, we serialize first, then we chunk, then we hash everything and create the index at the same time. Then we compress it and store it somewhere. If we want to extract one of these things, we do the opposite, right? We acquire the index file, we go through the index file item by item, look for the chunk in the chunk store, uncompress it, concatenate the whole thing so that we have a serialization and deserialize it to disk. And that's really all there is. Yeah.
This is basically very similar to Git.
Well, I mean, Git doesn't do anything with the serialization, right? And Git also focuses very much. So one of the major differences here is that I don't care about the file boundary ultimately. I get rid of it very, very early on. Git cares, and Rsync too. They all care about the file boundary, right? So I think that is a weakness. I mean, it's a strength in some ways and weakness in others, because what Rsync and Git are never capable of is like they cannot really track when like content moves between files, right? It also has this, specifically in Rsync, that's a problem, right? Because Rsync is not capable of recognizing when you rename a file or something like that. Because like this algorithm, the Rsync algorithm is in Rsync only applied on individual files if both of them, like if they exist under the same name on both of sides. Then it's efficient, otherwise it's not. So this stuff, however, has this benefit, like I serialize first, then I forget everything about what I just serialized and the file boundary and anything like this, and chunk it up at that point, which has the nice benefit. Small files that get lumped together with other small files until I reach the average chunk size. And the big files are split up into small bits so that I reach the average chunk size. So yeah, and it has a nice benefits that, yeah, same files that move between directories I'll perfectly well recognize with this, because I only care about the data contents. I don't care about file boundaries or anything like this. So yeah, key difference to Rsync or Westry or Restic. I mean, there are many systems that use some of these bits. There's, at least to my knowledge, no system that uses this combination to build a system like this. But the key difference, yeah, forget the file boundary. I don't care about the file boundary. Limiting yourself by always keeping the file boundary in your mind makes a lot of things very difficult, like tracking changes across.
If we don't care about file boundaries, how do hard links work?
That's a very good question. By the way, I figure I should repeat those questions, right? So the question was, if we don't care about file boundaries, how do hard links work? I don't care about hard links, that's my answer. So, okay, it's not quite that easy. So I do care about hard links. Like, I thought about this for a long time, whether I should actually care about hard links and actually serialize the fact that they exist. Ultimately, they generally don't, right? Like, and if you tar up a Debian image or a Fedora image or something, you won't find many hard links in there. I use them though heavily. So there's a mode, an extraction mode, that I'll come to later, where you basically can use an existing tree that you already have on the system, and then extract a new version, and then if you want to, hard link the old version to the new version, so that you basically can have two versions of your image, and everything that's similar or identical is hard linked up, if you follow what I mean. But let's talk about that a little bit later again. Any other question at this point?
So a hash, you can have from some data 2 times the same hash. Okay, the change is small, but it can happen, right?
Yeah, so the question was about the hash collisions, right? Well, I mean, it's, yeah, it happens, sure, in theory, but we don't have enough atoms in this universe to make this, like, build a machine that can actually happen. I mean, it happens for SHA-1. This is a way stronger one, it's SHA-512/256. But if we live in a world where collisions actually happen, then we have a problem anyway with GIT and so on and everything else too, right? Like, before I have to think about that, a lot of other people had to think about that and fix it for them, and they just can copy the solution. Anything else in this point?
How does it handle repetitive data?
So how does it handle repetitive data? Within files themselves. So like this serialization, I mean, it reads all the files, and then if you have repetitive data within the same file, this will always result in the same chunk. So on the server, ultimately, the number of chunks ending up, like if you add them in by size, it will be much smaller, of course. Like, it will automatically recognize similarities or identicalities, whatever you call them, within files. It will identify them across files, because it doesn't really care about files, right? Like, that's a good thing. So yeah, it's very efficient. Like, it will reduce, like, throw all the duplicates data around. Out. Like, of course, always within the average chunk size, right? Like, if you have identical data that is shorter than the average, well, minimal chunk size, then we'll never be able to find that, right? It's not for that. But yeah.
What was the name of the compression algorithm?
The name of the compression algorithm, that's ZSTD. It's a Facebook thing. Like, it's relatively good compressing and very fast. So.
But I guess you designed it to be swappable.
It is already swappable. Like, you can use XVAT and you can use something else too. But yeah, I mean, you can even, the hash function can replace that too. But the thing is, I wanted to, like, and you might even want to replace the hash function. Like, if you care about 32-bit processors, SHA-256 is way faster on those. So if that's what you care about, then you should probably swap that out. But I think most computers are probably 64-bit, so that's what we default to. Okay, let's continue. Yeah, so in an average, the chunks are evenly sized, and we can recognize similar blocks in different files. File renames this way, files moving this way. We can recognize the same file contents within files even too. And yeah, why do we all this? Similar file system images will result in mostly the same chunk files, and hence you get efficient storage of many related trees, and all that without keeping any kind of history. It's also, what's really nice about this is that everything is implicitly validated, right? Was that me? Weird. So everything is implicitly verified. So there's this DM Verity thing that some of you might... Oh, it reminds me that my talk has begun. That's nice. So there's the DM variety, some of you might heard of. It's a Linux kernel functionality that basically allows the system to validate every read access to the hard drive and guarantees cryptographically that what is being read is actually the version that whatever the vendor put together. This stuff will give implicitly similar behavior, right? Like, because we check everything against the index, and the index contains the cryptographically strong hash values of all the data blocks, all the chunks. We get the same behavior there, right? Like, we get the complete guarantee you won't be able to play games with us and provide us with wrong data, and we wouldn't notice. It's also relatively CDN friendly, like content delivery network friendly, because you know, roughly our chunks are always the same size, right? Like, and you can pick when you use casync what your average chunk size shall be. So since CDNs generally like, you pay for the number of objects requested or something like that, so you can actually pick like how much you want to pay to the CDN. Use larger chunks. That basically means fewer objects get requested by clients if they want to download something, but less similar patterns and the data will be recognized, right? Because the data gets a lot larger, we won't be able to deduplicate so much. So it's relatively CDN friendly. I mean, other systems, like for example OS3 as one, they traditionally started out at least as something where every individual file would get its hash and would be put on the HTTP server. So if you look at Etsy or something where you have these tons of very small files, Etsy hosts and whatever they're called, they would all get this little object, and you would have to pay CDN with millions and millions of GET requests because every client requested that. Their way out of that problem was adding binary deltas. Binary delta is actually something very opposed to what I'm doing here, because binary deltas between different versions always implies history, right? You need to keep history. You need to have somebody who sits down and figures out what are the image versions that it's worth updating between, so that he pre-calculates the diff and puts it on the server, right? So this is management work. With this stuff, nothing of that sort is required, right? Like, every image stands for its own, and if data blocks are reused, that's automatically detected, because I don't care about history. I don't care about anyone managing anything. I just care about the chunks, and they automatically, out of themselves, deduplicate themselves. Any questions otherwise? So why all this? Yeah, when acquiring a new image, we can actually take benefit of the fact that usually, like, if you do an operating system upgrade, you already have one version, right? Like, that's the definition of an upgrade. So we can actually go over the file system and do the same algorithm that was just explained, and then we'll get a list of hashes that we already have, that we can read on the version that we already have. And then when we do an update, we just copy it from the file system that we already have into the new version that we're about to create. And only the chunks that we don't have yet, we actually acquire from the internet. So yeah, basically with everything that we have, we get a pool of reusable chunks. Interesting thing about this, that this actually allows even updating efficiently, or relatively efficiently, between theoretically foreign like images. Like, for example, you could actually tell casync to use your Debian image as a base for installing the new version of your Fedora image, right? And the sync would automatically recognize the similarities. And there are some. I mean, it's not going to be as efficient if they actually share some common history, but it will recognize what the similarities, like time zone data and locale data, which tends to change relatively seldomly. So, which is kind of nice, right? Like, because you don't need any actual historical relationship. If there is one, that translates to better efficiency, but yeah, you can actually throw any kind of tree on it, and casync will recognize the similarities, and if there aren't, then it doesn't hurt. It just makes it a little bit slower initially because we have to index everything, but other than that, it doesn't cost you anything. Yeah, so there's automatic robust reusing of what's downloaded before, right? Because everything is cryptographically verified, even if you have like the old version was modified locally because somebody hacked it or whatever else, we wouldn't use it, right? Like, we wouldn't use it because we read the stuff from disk, hash it up again, and check it against what we expect it to be. And if it's not, we just don't use it and use the data from the internet instead. Anyway.
You said at the beginning that you can choose the chunk size on average, right? So I guess if you choose like the smaller size, the chance of reusability are pretty much higher. So what's the trade-off, and how do you choose that size?
That's a very good question. It really depends on your use case. What the by the way, the question was regarding chunk sizes and how do you choose the right chunk sizes for what you want to do, and what the trade-offs are. Yeah, I can't really give you the perfect answer for that because it really depends on what you're doing, and for many use cases I don't have any answer at all. But yeah, as mentioned, I don't know, for the backup case, for example, things will be very, very different than for the image delivery case. And for the image delivery case, it really depends what you actually ship. Like, for example, some people ship SquashFS. I actually have a slide about this later. SquashFS in theory is very much contradictory to this concept because SquashFS removes redundancy anyway. So I won't recognize any data within it. And in theory, if you have fully compressed data, then yeah, every change in the beginning will explode into the rest of the image anyway. Now, SquashFS thankfully isn't like that because SquashFS still needs to be a random access file system. So what they actually do is they compress a little, and then they stop the compression, restart the compression for the next stuff, and then add an index at the end. So because that is that way, if you synchronize things properly with casync's chunking, right, like the block size that SquashFS uses and the chunking size that casync uses, you can actually even deliver SquashFS relatively efficiently. But if you're asking me now what the right settings there is, I can't really tell you that because it depends on your use case, and people have to crunch the numbers first to figure out what's right for them. Now, this is actually something that the other talk on the other end of the venue here is doing. Like, he actually put a lot of container images on casync and tried to figure out when this actually starts making a lot of sense and when it doesn't do so much. And he gave me a quick overview about the results of this. But yeah, if you want the answer for the question, you have to go to the other talk, I guess.
Can we, in this case, about this question, can we have index for different chunk sizes? I mean, in one place?
So the question was regarding, can we have at the same place index files for different chunk sizes? Yeah. So I mean, sure you can do everything, right? Like casync won't stop you. But of course, if you operate with different chunk sizes, casync will chunk at different places. So actually, I mean, it's not that you could reuse chunks. It's very unlikely that you can reuse chunks because we will chunk differently ultimately, right? But you can place them. But honestly, before you deploy casync, you should do your homework and figure out what the perfect chunk size for your stuff is. Ultimately, I mean, it's not that it's completely have to be set in stone, right? Like, you can change it later. It won't hurt you technically. It will only hurt you that, yeah, when you do fiddle around with the chunk size all the time over the progress of your project, each time you do it, the level of reuse for the chunks goes to zero usually. But it's not that it's like it won't create technical problems. It will just, if you fiddle too much, then the bandwidth savings that this is supposed to provide you will not be delivered.
So in principle, could you update, for say, live IoT devices with a new image? If so, what may be the gotchas on that one?
So the question was regarding updating live IoT images with this, and what the gotchas are about doing this. So this is definitely one of the use cases, right? Like, you saw the IoT on the thing, and well, I mean, if you do the double buffering thing, like the AB partition stuff, right? This should be pretty well. Like, it really depends what your constraints are. Do you actually care about runtime for this, or do you not? Like, do you care that, like, I mean, it will, like, if we try to, like, if you take benefit of the seeding stuff, like, seeding is how I call this, that you look at the operating system version you already have and chop it up and use it as a pool of chunks. That of course takes a lot of time, right? Like indexing all of that, and you could cache the results of the indexing, but if you actually have file system trees that change, then the cache, like, we can't maintain this. There's no sufficient API in Linux how we can detect changes on the block layer, at least. On the file system layer, that's not so much of a problem. But yeah, if you want a one-stop solution that already is well tested and people know exactly what the parameters are that you want to put in there, then casync is not for you. But yeah, this is stuff that's still relatively new. I know that a lot of people have been doing this. As I learned recently, there's even a re-implementation of the casync client side, at least in Go, that nobody told me about until yesterday. And so apparently there's some adoption, but ultimately most of the code is less old than a year, right? So yeah, I think my answer is definitely, it's absolutely the use case for this, right? It's actually what I care about. It's actually what I want to build is like a self-updating stuff where people are a little bit smarter than just DDing things around or tarring things around. But it's not a ready-made solution. Like it's not a product. It's a building block that you have to make fit to whatever you want to have.
There was a talk yesterday on exactly that, like doing a few partition updates and using casync as the network backend.
Oh, there was another one about this. Oh, good that I know now. Who did that? Oh, the Pengutronics people. Oh, awesome. Yeah, okay, they're great people. Anyway, I probably should watch the video about that and the other one. 3 casync talks at the same conference is awesome. Anyway, if nobody has questions, let's continue with the slides. Yeah, this is something I really wanted to stress. There's no revision control. I already mentioned this, right? Like this problem with what OS Tree tried to solve by having binary deltas between the key versions that people want to download, upgrade with. This is not necessary at all. There is no revision control. Revision control is a useful thing for developers, I think, but for deployment, I think it's a weakness. I think, for example, it's a weakness of the Docker model, for example, because they have these layers, which are two things. They on one side, they are revision control for developers, right? So that they start from the Debian thing and then they make their changes. But on the other hand, they also are their way how they want to reduce downloads, right? Like because everybody already has the Ubuntu version, people don't need to download that. I don't think you should intermix that ever. And since this is about delivery primarily and not supposed to be another Git, like not supposed to be revision control, the emphasis is really, yeah, there has to be no history and you don't have to manage anything. And it's all standalone individual thing. And if two people happen to have the same data somewhere and share no history together, the same chunks will be recognized anyway, regardless. Yeah, forget revision control. And we find the similarities automatically. Revision control is for developers, it's not for deployment. Then, I already mentioned that I'm not using tar. I'm using CA-tar, this little thing that I came up with. It's strictly reproducible, right? There's only one valid serialization with CA-tar of a directory tree. This stuff is defined so that it could actually be tar 2.0, like all the warts of tar removed, but then again, I'm not pushing for that. That's not the problem we're trying to solve. There's random access. It has a couple, like the random access thing is awesome because it basically allows casync to mount these index files remotely into the local file system via Fuse. And then in the background, I can download the chunks as I need them, as the client accesses them. And because I have random access, I can give you proper file system there that basically ends up on your local system incrementally as you use it. The random access thing is something very much a shortcoming of tar. There are a couple of other things, by the way. Like I care a lot about metadata control. So metadata control means like depending on your use case, you need different metadata in your archive. Like for example, if you do an IoT container image, you generally don't care about M times, like modification times, because M times are a bad thing for that thing because they contradict reproducibility, right? Like if you put together your image today with GCC and RPM or whatever else, and generate the exact same bytes on disk, they will still have different M times than if you do it the tomorrow, right? Like because the modification times will then be the ones of tomorrow. So if you do container or IoT images, you generally don't want M times because they mean changes that you're not interested in. If you, however, do a backup of your home directory, you very much care about M times. They're actually a useful thing to figure out, like on what date did you work on which document. So in CA-tar, I actually do care a lot about that, so that you can explicitly pick the metadata that is actually included in serialization. And that's kind of, for me, a requirement also for the reproducibility, right? So that if you actually are in control whether to store M times, whether to store user access modes, whether user identities like chown and things like that, whether we store ACLs or extended attributes, all the things, only when you're in control you can actually make sense of the reproducibility there. The metadata that we store is very comprehensive. I don't know any tool that goes into that much detail because we store all the weird stuff that we have nowadays in Linux, like these file attributes like the chapter stuff and I don't know, quota, project IDs and all the exotic weirdness that we have nowadays. Yeah. Any further question at this point? That's one.
If you're mounting your casync archive, is that read-only or?
That's read-only. Like all of this is about reproducibility, all about immutability, so that every access is validated all the time through this index thing, and that basically means everything's read-only, right? So if you're looking for a general-purpose file system, this is not it. This is an archive format. This is a image delivery format and a cryptography secure one. When you actually play around with casync, you'll see a couple of different files. The primary one is CAIDX, that's the index file. It is, as mentioned, just a list of hashes with the offsets or the lengths of the individual chunks. There's something CAIDX, exactly the same thing internally. The difference is only semantically. Like one is that if you operate on the block level, and the other one if you operate on the file system level, right? CA-tar, already mentioned that, it's pretty much the same thing as tar, except that it has reproducibility, file system attributes, random access, and these kind of things. And then there's .castr, which is a chunk store directory. So it's not a file, it's a directory, and that's where, if you actually go in there, you'll see a lot of little files, all named after hashes, that if you actually look into them, you see that they're all ZSTD compressed, and if you decompress them and use OpenSSL to calculate the hash, so you'll figure out that, yeah, they map there exactly the file name they're stored under. So if you actually come into contact with this, these are the 4 things that you will see. There are a couple of more actually like this, but these are the ones that actually matter.
So does that mean that when you do a casync, the space of your system is going to grow up?
Sorry?
Does it mean that when you sync, because you are creating the CASTR, does it mean that your file system grows? Because you have to generate all that hashes which contains the...
So the question is regarding if my local file system grows if I do use this. So casync can store stuff locally if you want to. Then of course you will have to pay for the local store. But it can actually do the same thing remotely. Right now only through SSH to some other site. And in that case we store a little bit of temporary data, but that's not substantial data. That's a little bit. So the idea really is when you create an archive like this, we send to the other side a list of chunks that we would like to store there. And then the other side tells us, oh, I already have these chunks, but these ones I still need, and then we send them the ones that it still needs. So it's relatively efficient there. But then again, like so far it was optimized about making delivery cheap, not about making creation cheap, right? Like not about the archiving step, but of the extracting step. This is changing now as I'm looking into solving the backup thing more, because in the backup thing more, suddenly the archiving thing becomes like the big problem because it needs to be fast and things like that.
But those temporary files do not really take up much space.
Yeah, they probably take up, I don't know, 10 megabytes at most or something.
So after you create this index file and some change appear, does the second round be faster somehow? Will it reuse the index file or it will take the same time as?
Okay, so the question was regarding if we generate an index file, then the change is made on the directory and we generate another index file, do we take benefit of the fact that we already indexed it once? The answer to that is yes, since yesterday. So it's a big thing. Like if we actually care about the backup case, right? This is what we need to optimize for, right? Like I want to go for high frequency backup. So what I'm really hoping to deliver eventually is that we can do your home directory every 5 minutes or so. You do backup and you don't have to pay for it massive amounts of time. Linux or Unix makes it really, really hard because we don't know what files have changed. There is no generally accepted API for doing that. Like Btrfs is something like that, but it doesn't really work. And who uses Btrfs anyway? And the other ones don't have that at all. So what we actually do is we do what Git does and what everybody else does as well. We stop the whole tree and see what has actually changed. We try to be a little bit smarter than most people, though. We use file system generation counters, which is a little known feature that most file systems on Linux at least have. Nobody knows how precisely they're actually really defined, but the essence is that supposedly in every change you make to a file, they are increased in some way, and so if they haven't changed, then you can use that to know that they haven't changed, right? So since yesterday is when my colleague emerged my patch that took benefit of that, we have this caching thing in place where basically, yeah, so for the first, like in the first iteration, we serialize the whole thing as I explained, but then we store information that last time I looked at this file in this version, this mtime inode and generation counter, it hashed to this thing, and by the way, in the chunk that refers to this hash, there's also this and this and this and this files with this inode number, mtime, blah blah blah, and then I verify that if that's still the case, and if that is the case, then I just use the hash, and I don't have to actually read stuff off disk. I don't actually have to hash it again. I don't actually have to compress it again. So yes, we do take benefit of that now, since yesterday when the patch was merged.
You looked at the Borg backup to see how it does backup?
Like BUP?
Borg? B-O-R?
Yes. So the question was if I looked at the Borg backup. Yes. I mean, a couple of systems that are like this, they all end up the same thing. We have nothing in this area. Like, ideally, if Linux was like a really good operating system, we had some better APIs for this. Like, for example, recursive mtime. It's a thing that 15 years ago people already wanted this and still not there. And people want that for search engines. People want this for backup solutions. If it was there, I would so love to use it. Because we don't have recursive mtime, we have to descend in the entire tree, start everything, and sucks. Thankfully, Linux has been optimized for that thing because that's what everybody does, right? So that's why git start is actually pretty fast. If it wasn't, then yeah, people wouldn't be fans of git so much.
An index file and the store is on a CDN. Do you store a reference to the CDN inside the index, or how do you find the store?
So the question was regarding like how are the index files and the stores linked up? They aren't. The idea really is that the data can come from everywhere, and you have to tell casync when you invoke it which stores it shall be using. It can use any number of stores. The idea is even that later on, like it can use local seeds. That means like local versions that you already have. It can use stores, but ultimately I want to go to some point where like we have a multicast protocol that on the local broadcast domain of your network can actually ask for these blocks as well. So the idea is basically that if you have this big cloud thingy installation where every node runs the same operating system, that instead of every single node downloading the new version of the operating system, they pick something, download it, and then for everything they constantly ask on a multicast for other blocks, and that would be perfectly safe even because it's all cryptographically secure, right? Like if somebody gives you bullshit data, you just calculate the hash, figure out it's not right, and throw it away. But the idea really is that, I mean, a model like this is not only useful for cloud, it's also for IoT devices, right? Like if you have lots of things like that. So yeah, there is on purpose no implicit connection between the chunk store and the index, because I want people to enable to get the chunks from wherever they like.
Yeah, building on that question and this idea of multicast, then have you considered as the next step DHT, and then eventually, you know, a BitTorrent clone essentially? I mean, what do you think?
Well, I mean, the question was regarding what's the next step after adding this multicast stuff. If we do something like BitTorrent or DHT stuff, well, I mean, it's not. You know, my focus right now is image delivery and backup. And for backup, I'm not even sure how you would use torrents like stuff there. But sure.
Go to the other talk. He wants to cover that.
Yeah, I mean, sure, there's lots of things possible, right? Like, but this is not finished yet, not even with the stuff that I'm doing. And then I have ideas about lots of things, but not even the multicast thing is in any way more than a thought somewhere.
You've been using iNotify to find files under your /home directory with a file change.
So the question was regarding iNotify, if we can use iNotify to get the notifications about changes. So iNotify is an awful API. Like, it's another one of those Linux file system APIs that suck. It's first of all, it's asynchronous, and it throws away stuff. And it throws away events. Like if the event queue is crowded, then it throws away. And then if you do, you're supposed to start everything anyway, right? Like so, then it doesn't do offline changes, right? So it basically means like if you took the hard disk out and put in some other device and made a change there, you will never. iNotify won't tell you about that, of course. And the biggest problem is it's not recursive, right? Like this is supposed to be for home directories that have a couple of gigabytes of size or terabytes, whatever else, and in deep directories. And iNotify does not work recursively, right? Like people try, and then they run out of inode handles, but it's not designed for that. It's just, no, it doesn't work. And also, I really don't want an online component, because online component means like it sucks for for like embedded stuff and things like that, right? I want a component that I look at the stuff as it's now and do the best out of it, and then I go away, and then eventually call me again and I do the best thing, and I don't have to stay around and watch whatever you do because that's evil. Anyway, there's more questions.
Which one of those files will you use for this online mounting of the fuse file system? So like, how do you mount
Where's my slide about this? Yeah, I had a slide about this. Oh, this is a slide, of course. So there's this slide here. That's what you can type. And then you see, like, you have this CA index. If you don't specify store explicitly, CA-sync is smart enough to look for the store next to where this is. So it will automatically make up the URL http://default.castr and look for the stores there. So that you have this one thing, and then if this just works, if you do this, then you get a directory somewhere, and then you can go into it and we'll download everything in the background. It's actually kind of nice, even because it does this progressively, but while you access it, like it has a prefetch thing in there, but while you access it, pulls those with a higher priority and things like that.
So the index is also a list of the content file names?
Well, the file names are the hashes, so there is nothing.
But the unpacked, deserialized files. So if you want to build a directory tree for the mount point, then where does that information come from? You don't serialize the entire chunk store. Deserialize it before you mount it.
So the question is regarding where does the directory tree information come when you do something like this? Basically, you know, like there are multiple layers here, right? Like there's the indexing, and the indexing I have a random access thing interface to that, right? Like I can basically say, give me byte 1,000,000 from my stream, and then I have a relatively efficient, like it's O of log n algorithm to figure out in which chunk it is, and then I can download that chunk from the internet wherever I have, and maybe I have it already, I don't know, and then within it. Because I have random access on the upper layer as well, in the tar layer as well, I just need to, like, basically the way how CA tar works there is that the file form is supposed to be composable, meaning that the serialization of a directory tree is strictly the serialization of all the stuff within it, concatenated, plus some header and footer, right? So it's strictly composable. The composability is a nice thing if we want to recognize stuff. But this basically means that there are never pointers from up to inner and from inner to upper, to outside, if you see what I mean. The random access stuff is reached by having at the end of every directory we have a little, like a bisection table, which we use to find the right file. So ultimately what happens there basically is that it's a little bit like a file system, but a weird file system, because I don't not only want random access while reading, I also want like a serialized access, efficient serialized access while writing and reading. So it's like this hybrid of something that is random access but also is streamable. Because the streamable functionality in tar is actually kind of nice, and I thought that would be nice to keep. So it's something like a file system, and then you have the upper layer and the lower level, and the upper layer figures out where to look, and the lower level then translates that to actual chunks that have to be requested through HTTP. I hope that answers your question.
Does that random access mean that you can just pull any part of an image individually?
Yes. So the question was regarding whether random access means that I can download any part of any image randomly.
It's implemented like in the CLI, like I want
yes.
just that direct.
Yes. So the question is whether you can extract parts of the archives, random parts, random subtrees, and yes, you can. I think I did not implement that here, though. Like you can't but it's not that it wasn't possible. It's just that it was too lazy. There's also, by the way, this thing here, casync make def. This is the same thing as the mounting, but on the block layer. So as you see, this mounts a CAIDX instead of a CAIDX. And then if you do this, you basically get a device in /def that is a block device like any other. You can mount it, you can look at it with whatever tool you like. And as you access it, it downloads stuff in the background and makes it available locally. It's kind of cool, actually. There are a couple of other nice things, by the way. We already mentioned that hard links are pretty cool. Like you can do that with your multiple trees. We also do ref links. How many minutes do you have? 5? So it does reflinks. Reflinks are this new file system concept. Like Btrfs has had that for ages, and now XFS is getting that too. Reflinks are basically a way how you can have two files in the file system and they share the same data on disk, so that the copies that you have don't come at the full price of actually being copies. And all of that in a copy and write fashion. So when you write to one of these two files, it gets automatically duplicated so that they don't interfere each other, which is massively different from hard links, because in hard links both ways into the file are identical, and if you change one, then the other one changes too. The hard link things is an optional thing because it has these effects. It basically means hard link. If you do the hard link stuff, then you can't ever write to the trees that you just extracted, because you will then also modify the other trees that you might have. The reflinks thing is, however, fully transparent to applications because of this copy and write nature that it has. It's actually really cool, this thing. Like the fact that I use Btrfs and I extract one of my images and then the other different version of my images. It's basically the disk space usage is like I don't know, 1% more I pay for each image version there, and otherwise it's identically in every way. I don't know about any backup system that can deliver anything like this, by the way. But yeah, cool stuff. Any questions otherwise at this point?
So you talk about Docker images, so this is large files. I'm wondering about is it also useful if you have, say, an IoT device which has a firmware size of 20 kilobytes or 100 kilobytes and a very slow connection to it. In your opinion, would this be useful?
Well, so the question was regarding whether this is suitable in very constrained systems, right? Like where you have very little space and very little time, right? Like, I don't know, this is not the world I live in, right? Like, I generally, this is not optimized for utter minimalism, right? This relies on OpenSSL and these kind of things, and I mean, it's not that we pull in millions of dependencies, but we do pull in OpenSSL at minimum and libACL and these kind of things, and the stuff it does, like it calculates hashes and compresses and these kind of things, it's not optimized for the tiniest bit. That said, I'm pretty sure it's fine for anything like ARM, like the regular ARM embedded device that you find. It should be fine for Raspberry Pi perfectly. But if you're talking about microcontrollers, no, forget that. So yeah.
On the backup case, will you have encryption?
Yeah, that's a big thing. So let me quickly, I got like 2 minutes or something. 3 minutes. Reproducibility matters a lot to me. So here, actually, because we can serialize that stuff and because it is so perfectly reproducibility, there's actually these two commands, digest and mtree. And if you run those on any directory, it will actually calculate a digest for you that identifies that version of the tree perfectly. So what this actually does, it CA tars it up, throws away all the data, but calculates the SHA-SUM over it. So it's a very nice way how you can get a SHA for some directory and to see if the directory managed in any way. So it's completely out of scope for the rest of things, but it's kind of nice to have. casync mtree is similar to this. Mtree is a format that the FreeBSD people came up with. It's a manifest tree. It basically, it's a list of files and directories that should be there and where the contents should have this hash and where the metadata should be this and this and this, and casync mtree allows you to very efficiently generate the same thing from a CA index or from a raw file system. So I don't know, it's kind of useful, this stuff. It's kind of the fringes of what we do. It's a side effect that we can do this very easily, but it's interesting to mention still. Casync can do local operation, like directly to file system. It can download from FTP, HTTP, HTTPS, FTP, like the usual SIT and SFTP. It can upload currently only through SSH, but that's not because I didn't want to support that, but mostly because I didn't find the time to yet. The idea is that later on maybe we get backends for S3 or whatever else, so that you can do a local backup and put it on Amazon or whatever you like. So this is interesting. It does UID git shifting for those few people who use containers with user namespaces. They want to go into details there. One other thing that's actually kind of nice is like when you operate on the block device layer, usually the file systems that you store on your block devices are way smaller than the block devices themselves. Like for example, you have squashfs and it's compressed, but the partition you put it in, usually you have at least twice the size because you want to have some room for upgrades and things like that. This is annoying for things like this, right? Like because if you, like depending on big the SD card or whatever it is you have in your embedded device is, you might end up with completely different partitions, right? Like because there might be different amounts of space behind that, and the space might not be initialized, or might be, who knows. Anyway, casync is relatively smart. It actually can read the size from the file system, so it has a minimal parser for a couple of important file system headers and figures out the actual size of the file system, so it can do stuff. So the last bit is about the future, and that's the encryption stuff. Over Christmas I actually sat down with my brother, who's a crypto postdoc, about figuring out how we do the cryptography. So he'll get a paper out of it, and I'll get the crypto system that will hopefully convince people enough. But the idea, yes, there's going to be crypto, and it's going to be strong crypto, and it's going to be. The idea is basically I want to go for this model that if people use it for the home directory, they can store it on servers that they don't have to trust, and those servers don't know what they're storing, and they have no way to figure it out. Yeah, the information is all available on the client side, and we will still duplicate at least between you, but potentially also with others. Anyway, no time anymore, right? But one question?
One question, yeah.
One question?
What about preserving, saving, and restoring some fancy file labels like Linux or whatever?
Yeah, the question was regarding what about saving, restoring fancy file metadata like as a Linux label. As mentioned, metadata control is important. So if you look at this, there's actually, I have this one slide here. Metadata controls, and like you have these dash with and dash without things, and on these arguments you list explicitly the metadata you want to store and the metadata you wouldn't want to store. And there's a ton of metadata. There is, as a Linux label, so extended attribute, there's project quota, there's UIDs, whatever you like, and then you, depending on your use case, you say which ones you want and which ones you don't want, right? And like for the home directory backup thing, you would probably say, I'm not interested in user identity because the stuff is owned by you anyway, but you do want times. For the IoT thing, you say, oh, I care about ownership, file ownership, but I do not care about the trees. So you pick specifically what you want, and I think there are about like 40 or so different bits that you can pick. Anyway, I think that's my time. Thank you very much. If you have any questions, ask them very soon because I'm heading off to the airport. And yeah, unfortunately, you couldn't see the other talk, which I would really have loved to see. But thank you.